Pelton, Francis, and Kaplan are the most commonly used hydraulic turbines. In this video, we will compare these three turbines and see when to use which turbine. When we move from Pelton to Kaplan, the force-producing mechanism changes from impulse to reaction. In Pelton, pure impulse force of water jet is responsible for rotation of impeller. Water stored at high altitude can produce high impulse force due to its high velocity. So Pelton turbine are suitable for operation when water energy is available at high head and low flow rate. Whereas Kaplan turbine is suitable for the reverse case. A high water flow will guarantee efficient production of reaction force. So when water is available at high flow rate and low head, Kaplan turbine is the best choice. Francis turbine comes in between for medium head to medium flow rate applications. Francis turbine is not a pure reaction turbine. A portion of force comes from impulse action also. This graph gives a clear idea about when to use which turbine, depending upon available water head and flow rate. It is obvious that Francis turbine covers a wide range of operating conditions, or they can work efficiently in wide range of operating conditions. This is why Francis turbine is the most preferred hydraulic turbine. If you use a turbine out of its recommended operating range, it will work, but less efficiently. It is also interesting to note the direction of fluid flow with respect to axis of rotation in each case.
Welcome to the video tutorials of Mechanismuller. This animation authored by Dr. Seyhan Ersoy is the property of the client Mec.Fluidos and subject to copyright limitations. We thank Mec.Fluidos for giving us the permission to publish this video. There are three major types of water turbines. The Pelton turbine requires large water head and low flow rate, and the Kaplan turbines require low water head but large flow rate. The Pelton turbines usually build in mountainous regions, while the Kaplan turbines are located in lowlands. These restrictions make these two-kind turbines less common than the Francis turbine. The Francis turbine fills a large gap between the Pelton and Kaplan and it is widely used. They operate in water head from 10 to 600 meters, and primarily used for electric power generation. Their power output can be calculated from the water head and flow rate and typically range from 10 to more than 700 megawatts. One of the distinct advantages of the Francis turbine with respect to other water turbine is that they can also be used as water pump. This makes them ideal for the pump storage systems. This animation shows the operation of a Francis turbine in a dam. The arrows show the water path and direction inside the dam. The water from reservoir behind the dam transferred to the turbine by a penstock. The penstock diameter of a Francis turbine could be as large as 10 meters. The water coming from the penstock is transferred to the inlet scroll, which distributes the water equally around the wicket gates. Water passes through the wicket gates, which controls the amount of water passing through the turbine, before reaching to the runner. This in effect controls the power output of the dam. Wicket gates also adjust the angle of the water reaching to the runner. After passing through the wicket gates, the water reaches to the runner. The water pressure forces the runner to rotate. The rotation speed of the runner can be in the range of 80 to 1000 revolution per minute. The water continues its motion downward under the runner to the exit pipe. The exit pipe discharges the water to the environment as low-pressure water. The turbine shaft of the Francis turbines is almost always mounted vertically. This makes discharge of the water much easier due to swirling effect of the water, in the inlet scroll, and the effect of the gravity. The rotation motion of the runner is transferred to an electric generator shown in here. The generated electricity is converted to high voltage current and transferred to the grid to be consumed. One big advantage of the water turbines is that power output can be regulated very easily. If the demand is reduced, the amount of water flowing to the turbine can be reduced relatively short period of time. We thank our client Mec.Fluidos as giving us the permission to publish this video. We also thank our viewers for their continuing support of our channel.